Hello and welcome to today's lesson on contact and non-contact forces, which is part of the forces topic in GCSE Separate Science Physics. So in today's lesson we're going to understand what the different types of forces are in the universe. So if we are successful and learn in today's lesson, we should be able to state Newton's laws of motion, relate Newton's laws of motion to different situations, and understand the difference between contact and non-contact forces, which links into the following part of the GCSE Separate Science Physics Specification 4.5.1.2 Contact and Non-Contact Forces. So we can demonstrate forces in many different situations, such as when an object is being pulled, such as when an object is being pushed, such as when an object is being accelerated, and such as when an object is being stretched. Now, there are many different examples of forces in our universe, such as the electrostatic force, the gravitational force, air resistance, thrust, tension, a magnetic force, frictional force, and the normal contact force. So a force is a push or a pull that acts on an object due to the interaction with another object, and the unit of force is the Newton, and all forces are vector quantities, so they must be given a magnitude and an associated direction. Now, the following demonstration of a paperclip being levitated near a magnet or a magnet levitating near another magnet indicates to us that not all forces have to be contact. Some forces can be non-contact. This means objects do not have to be touching each other to exert a force on each other. Now, examples of this include the gravitational force, the electrostatic force, and the magnetic force. So an example of this would be the fact that the Earth and the Sun are not touching each other, yet there's still a gravitational force between them. This shows us that the gravitational force is a non-contact force, yet some forces do need objects to be in contact with each other to exist. These are called contact forces, and examples include friction, the reaction force, and tension. So for example, the ball and the surface in this example are rubbing against each other. The bumps in each prevents a smooth movement between the two, so this contact provides a frictional force. Another example would be the reaction force. So here the surface is providing an upwards force on the ball to stop the ball falling through it and hitting the ground. So this contact provides the reaction force. Another example would be tension, because in this example the ball is pulling down on a cable and this causes the cable to stretch out. So this contact provides the tension or tensile force. So we can categorize all forces as either contact or non-contact forces. So the contact forces include friction, air resistance, tension, the normal force, and these forces occur when objects are physically touching each other, whilst the gravitational force, the magnetic force, the electrostatic force can occur when the objects are physically separated. So all forces between objects are either contact forces, forces that occur when the objects are physically touching. Examples include friction, air resistance, tension, and the normal force. Or they could be non-contact forces, forces that occur when the objects are physically separated. Examples include the gravitational force, the electrostatic force, and the magnetic force. So if objects do not have to be in contact with each other to exert a force, how do we represent the area in which a non-contact force can act within? Well, we can do this in physics by saying objects can exert non-contact forces by exerting a field into space. Now, a field is a region of space where a body can feel a non-contact force. So for example, the Earth's gravitational field is a region around the Earth where you can experience the Earth's gravitational force, and we represent fields with field lines. Now, the strength of a field line is given by its field density, how many field lines are found in an area or how close the field lines are to each other. So in a gravitational field, the closer you are to the object making the field, the denser the field lines, the stronger the non-contact force experienced. In an electrical field, the closer you are to the object making the field, the closer the field lines are to each other, the stronger the non-contact force experienced. Now, as a note, in an electrical field, the field lines point in the direction a positive charge would move in. So the strength of a field is given by how many field lines are found in a particular area. This indicates how strong a magnet is. Now, the correct name for magnetic field lines is magnetic flux, and the strength of the field is given by its flux density, how many field lines are found in an area. So the magnetic flux density tells you how strong a magnet is, and the unit of magnetic flux density is the Teslas. Now, understanding how forces interact with objects is very important, as it tells us how the object will behave in the universe. So for example, a pendulum can only be understood if we know the forces exerted by the pendulum. So it's extremely important to understand the rules on how forces interact with objects. Understanding the laws of forces allows physicists to understand and predict how objects will behave in the universe. So in 1687, Sir Isaac Newton devised 3 laws which dictate how all forces, contact or non-contact, interact in the universe. And so for every single situation in the universe, you can consider that you must understand that the objects obey Newton's laws of motion. So we use Newton's laws of motion to predict how all objects will behave in the universe, and we even use Newton's laws to predict where the planets are and where they will be in the future, which is how we can send spacecrafts to these planets to make measurements. So let's look at Newton's 3 laws of motion. Law 1, the law of inertia. Every object stays at a constant velocity when there's balanced forces on the object. If there is a resultant force on the object, it will either change speed or change direction. It will accelerate in the direction of the resultant force. Now, inertia is the idea that an object keeps at a constant velocity if no resultant force is acting on the object. So this is the physics behind how objects can accelerate or why they have inertia. Now the second law is that the resultant force in newtons is equal to the mass in kilograms times by the acceleration experienced in meters per second squared. So this is the physics behind how to calculate the acceleration experienced by an object. And finally, you've got the third law of motion, that when 2 objects interact with each other, they exert equal yet opposite forces of the same type on each other. And this is the physics behind how 2 objects can interact to cause both of the objects to accelerate. So let's consider again firstly the idea of law 1, the law of inertia. We've then got law 2, the resultant force is equal to the mass times by the acceleration, or as most commonly stated, F equals ma. And law 3, Newton's third law of motion, that when 2 objects interact with each other, they exert equal yet opposite forces of the same type on each other. So if we consider Newton's first law, what we've got to understand is that if there's no resultant force on an object, there is no acceleration. Now there can still be movement with no resultant force, but there cannot be any acceleration. So if there's no resultant force, it means the objects move with the same speed in the same direction. This principle is called inertia. Yet if there is a resultant force on an object, it will accelerate. So the acceleration happens in the same direction as the resultant force. Now a resultant force is the overall force on the object. Now remember, a resultant force causes acceleration. So in this example, we've got 60 newtons acting in one direction, 20 newtons in the other. So the resultant force is 60 newtons minus 20 newtons, which is 40 newtons. So we get an acceleration in the direction of the resultant force. Yet in this example, because 60 newtons will equal 60 newtons, there is no resultant force. This means that there's no acceleration on the object. The object stays at the same speed, which we call inertia. Now remember, Newton's third law states that when 2 objects interact, they exert equal and opposite forces of the same type on each other. Now for an acceleration to occur, there needs to be a resultant force on an object, not the pairs of objects, and this reaction force is only one force on the object. So if the forces on one object are the same, it would not accelerate. However, Newton's third law pair works on 2 objects, not 1. So here we need 2 objects to form a pair of forces for Newton's third law. So in this example, we've only got 1 object, a ball. So it can't be Newton's third law of motion. Here now we've got 2 objects, a ball and a ground. 2 objects are interacting. So the forces produced here are due to Newton's third law. Now it's important to note that if 2 objects interact, such as the ball and the ground, the forces will be the same size, but they'll act in opposite directions, but they will be the same type of force. So in this case, they're both the reaction force, but these forces will be acting on different objects. One is a reaction force from the ground to the ball, and the other is a reaction force from the ball to the ground. This means that both the ball and the ground would experience a resultant force and accelerate. So both would have that resultant force and acceleration. However, the two objects do not have the same acceleration because acceleration depends on mass and resultant force. So the more massive the object, the lower the acceleration experienced by the object, and the less massive the object, the higher the acceleration experienced by the object. So in this case, your ball, because it's a lot less massive than the ground, is going to experience a lot more acceleration. Now we can see Newton's third law of motion in many different situations in the real world. So for example, when a boxer punches at an opponent, his hand exerts a force of 100 newtons on the opponent's head, while the opponent's head exerts 100 newtons on the boxer's hand in the opposite direction, which is why boxers and fighters can break their hands when they have boxing matches, which is why they wear gloves. Also, Newton's third law can be very useful. It launches rockets, as the hot gas ignites in a rocket and it produces a thrust force downwards from the rocket to the earth. So because Newton's third law applies, because there's two objects, you are producing an equal thrust force from the earth to the rocket upwards. So you've got a resultant force on the earth and a resultant force on the rocket, and this causes our rocket to accelerate off into space. This means that rockets normally need a surface to launch off. They can't launch in space because you need two objects to produce Newton's third law pair forces. And finally, when you exert a push force down on the earth, Newton's third law produces an equal push force from the earth to you, and this produces the resultant force on you to accelerate you upwards when you jump off the earth. This means that when you move off the earth, the earth will move ever so slightly every time. Now when you push up on the earth, you will have pushed the earth down slightly. However, as the earth is very, very massive, the acceleration is tiny. Remember, acceleration is going to be force over mass. So because the mass of the earth is so large, the acceleration it experiences for that force is so small. Now calculations have shown us that even if all humans on earth lined up next to each other and jumped in unison, the acceleration on the earth caused by this will be too small to observe. So let's summarise what we know about Newton's third law pair forces. How are they similar? They are the same size with the same type, but they act in different directions and act on different objects. So let's summarise what we've learned in today's lesson. A force is a push or a pull that acts on an object due to the interaction with another object. All forces between objects are either contact forces, where the objects are physically touching, or non-contact forces, where the objects are physically separated. Now, example of contact forces include friction, air resistance, tension, and the normal contact force. Examples of non-contact forces are gravitational force, the electrostatic force, and the magnetic force. Now, force is a vector quantity, and you should be able to describe the interaction between pairs of objects which produce a force on each other, and the forces are represented as vectors. So if you've been successful and learnt in today's lesson, you should be able to state Newton's laws of motion, relate Newton's laws of motion to different situations, and understand the difference between contact and non-contact forces. So I hope you've enjoyed today's lesson, where we've looked at contact and non-contact forces in GCSE Separate Science Physics. Thank you very much for watching, and have a lovely day.